In this lecture, we'll solve two questions. In the first question, we find out of this pentagon ABCDE, and in the second question, we find out of this green shape. So we start with the first question. In the drawing, you have pentagon ABCDE. So what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interangles. This is pentagon ABCD. Pentagon ABCD is 5 sides: 1, 2, 3, 4, 5, and 5 interangles: 1, 2, 3, 4, 5. So in the drawing we have pentagon ABCDE, and we know that side ED equals to 1 unit in its length, side BC also equals to 1 unit in its length. This is side EA, this is also equal to 1 unit in its length. In addition, we know that side DC equals to x units in its length, and side AB equals to 1 minus x units in its length. This is angle AEB, this is right angle. This is angle ADC, EDC, this is also right angle. Again, our task is to find out the area of this pentagon, pentagon ABCDE. So first of all, we join points E and B together by straight line. We join points E and C together by straight line. In the next step, we'll extend side BA of this pentagon ABCD by straight line in such a way that the extended part will be equal to x units in its length. We define this point as M. You can again that AEM equals to x units in its length according to our construction. When you extend a straight line by straight line, the result is a straight line. So we extend the straight line BA by straight line, so the result BM is a straight line. So if you focus on the upper side of the straight line BM at point A, here the sum of the areas must be equal to 180 degrees according to all three. All three states that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM is point A, we have this angle that is right angle, plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, we join points E and M together by straight line. By joining points E and M, we get it by EAM. So in the next step, we prove that those two right triangles can relate to each other according to side angle side rule. So we prove those two right triangles in the new page, and we prove that those two right triangles can relate to each other according to side angle side rule. Okay, those are the two addresses, EAM and ECD, that are going to the original domain. So what those two addresses can go into each other? First of all, those two sides are both equal to x and therefore they are equal to each other. That is to say, MA equals to CD equals to x. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So this is angle EAM. The right angle EAM equals to angle, this angle EDC, and the right angle EDC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to 1 and therefore they are equal to each other. This is side EA, the right angle EAM, and it is equal to this side that is ED, the right angle EDC. They are both equal to 1 and therefore they are equal to each other. So if we prove that those two right angles can go into each other according to side angle side rule. That is to say, we can prove that those two sides and the angle that is included between those two sides in the right angle EDC are corresponding equal to those two sides and the angle that is included between those two sides in the right angle AEM. And therefore those two right angles can go into each other according to side angle side rule. So if you don't, if you follow that the right angle AEM congruent, this is the sum congruent to the right angle ECD according to side angle side rule. And from the fact that those two right angles can go into each other, first of all, we derive that they have also the same areas. Any two triangles that can go into each other, they must have also the same areas. So, okay, the area of this right wing triangle EDC is equal to the area of this right triangle EAM because of the fact that it can go into each other. They can go into each other, therefore they must have also the same areas. So if we define the area of this right triangle, the right wing triangle EDC as Z, then the area of this green right triangle EAM must be also equal to Z squared inside because they can go into each other, therefore they must have also the same areas. In addition, because of the fact that those two right sides can go into each other, we will derive that side EM is equal to side EC according to the rule that corresponding sides that can go into triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides, that is to say EM and EC, must be also equal to each other in their lengths. So if you hold that the side EM, the right triangle EAM, is equal to side EC, the right triangle ECD. The next step, we calculate the length of this side MB. MB in total equals to MA plus AB. So write it down, MB equals to MA plus AB. So MB in total equals to MA, that is X, plus AB, that is 1 minus X. So in total MB equals to X minus X is 0, so we left only with 1. So in total, if you follow that MB equals to 1 units in its length. MB equals to 1. The next step, we prove that triangle MEB can go into this triangle BEC according to side also. I copied those two triangles in the page and report that they can go into each other according to side rule. You can see that side EB is the common side that belongs to both triangles. So actually, also triangles E and B, EBC to the points on the original drawing. So what those two triangles can go into each other? First of all, those two sides are equal to each other according to what we already found out. That. So that is to say, side EM of triangle EMB is equal to side AC of this triangle EBC. So write it down. EM equals to EC. In addition, those two sides are both equal to 1 and therefore they are equal to each other. So EMB triangle EMB is equal to BC in triangle EBC. And finally, EB is the common side that belongs to both triangles. This is side EB, this is the common side that belongs to both triangles. So can I write down that EB equals to itself as a common side that belongs to both triangles. So if you prove that all the three sides of this triangle ECB are corresponding equal to all the three sides of this triangle EMB, therefore those two triangles can go into each other according to side rule. So at the moment, if you found out that triangle EMB can go in, this is the center can go in, so triangle EBC according to side rule. And for the fact that those two triangles can go into each other, we will derive that they have also the same areas. That is to say, the area of this triangle EMB is equal to the area of this triangle EBC. So write it down. If you found out that the area of triangle EBM is equal to the area of this triangle EBC. Again, if you found out that the area of triangle EBM equal to the area of triangle EBC. The next step, we calculate the area of this triangle by EMB. The area of any triangle equals to the base of the triangle times the height over 2. The base is MB times the height is EA divided by 2. So in total, we shall know that the area of this triangle EMB is equal to MB times EA over 2. MB is 1 times EA. EA is also 1 divided by 2. So in total, we shall know that the area of this side MEB is equal to 1 times 1 over 2. 1 times 1 is 1, so it is 1 over 2. It is 1 half. The area of triangle EMB equals to 1 half. So can I tell that the area of triangle EMB equals to 1 half? Let's hold this equation. 1 half equals to the area of triangle EMB equals to the area of triangle EBC. We grab that the area of triangle EBC also equal to 1 half. And therefore, the area of triangle EMB plus the area of triangle EBC must be equal to 1 half plus 1 half, that is 1. So, as you know, we should know that the sum of the areas of those two triangles EMB, MEB and triangle EBC, so that the sum of those two areas is equal to 1. So the area of triangle EMB plus the area of this triangle EBC is equal to 1 half plus 1 half, that is 1. Because again, we should follow that the area of triangle MEB plus the area of triangle EBC, in total, the sum of the areas of those two triangles is equal to 1. The big quadrilateral MEBC consists of those two triangles. Again, the big quadrilateral MEBC consists of this side EMB, this side EBC. And we already found out that the sum of the areas of those two triangles is equal to 1. Therefore, the area of triangle EMBC must be equal to the sum of the areas of the shapes that it consists of. That is to say, it must be equal to 1 half plus 1 half, that is 1. So we should find out that the area of the big quadrilateral EMBC, in total, it is equal to 1 square unit in size. And again, the area of the big quadrilateral EMBC is equal to 1 square units. But the area of this big quadrilateral EMBC, actually quadrilateral EMBC consists of two shapes. It consists of this right triangle EMA and this quadrilateral EABC. And because of the fact that the area of the big quadrilateral EMBC equals to 1, it means that the area of the quadrilateral EMA plus the area of this quadrilateral ABC must be also equal to 1 because of the fact that the sum of the areas of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. And we already found out that the area of quadrilateral EMBC equals to 1, and therefore the area of the triangle EMA plus the area of this quadrilateral EABC must be also equal to 1. So the area of the great right triangle EAM plus the area of this quadrilateral ABCE is equal to 1 because of the fact that quadrilateral EMBC consists of those two shapes, and we already found out that the area of quadrilateral EMBC equals to 1. Therefore, the area of the green right triangle EAM plus the area of quadrilateral ABCE equals to 1. But we already found out, according to our definition, the area of this great right triangle EMA equals to Z. So we can substitute the area of triangle EAM by Z. So we get that Z plus the area of quadrilateral ABCE in total it is equal to 1. Our task is to find out the area of this pentagon ABCDE. So what is the area of pentagon ABCDE? Actually, pentagon ABCDE consists of two shapes. It consists this great right triangle ADC, and it also consists of this quadrilateral ABCE. And therefore, the area of the big pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. Therefore, the area of pentagon ABCDE must be equal to the area of this right triangle EDA plus the area of this quadrilateral ABCE. And again, if you found out that the area of pentagon ABCDE is equal to the area of the great right triangle EDA plus the area of quadrilateral ABCE. But according to our definition, the area of this great right triangle EDC equals to Z. So we can substitute the area of the EDC by Z plus the area of quadrilateral ABCE. So in total, we should find out that the area of pentagon ABCDE is equal to Z plus the area of quadrilateral ABCE. But we already found out that Z plus the area of quadrilateral ABCE equals to 1. So we can write here that Z plus the area of quadrilateral ABCE equals to 1. And from this local equation, we derive that the area of pentagon ABCDE is equal to 1. So we found out that the area that we are working for this question, that is the area of pentagon ABCDE is equal to 1. One square is in its size. The area of this big pentagon ABCDE is equal to 1 square in its size. So we finish with the second question. In the next step, after the lecture, we'll start with the first question, of course. Okay, we finished with the first question. So, in the next step, I present you with the second question and solve the second question of this lecture. The second question, our task is to find out the area of this green shape. The green shape is actually triangle A and B, so we have to find out the area of the green triangle A and B. So in the drawing we have a circle. It is given as a question that AB is the diameter of the circle. In addition, we know that AP equals to 9 and BQ equals to 4 and AP equals to 9. We know that this is again APM, this is a right angle, and this is again BQM, this is also a right angle. Again, our task is to find out the area of actually the green triangle A and B. So first of all, we define the center of this circle, this point O. OA is the radius of the circle that we define as R. OB is also the radius of the circle that is equal to R. Here we can implement rule 7. Repeat quickly rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees. In the drawing, we have a circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of the circle, and according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. One put in our drawing. This is peripheral angle A and B that subtend on chord AB, that is the diameter of the circle, and therefore according to rule 7, peripheral angle A and B must be equal to 90 degrees in its size. So this angle is right angle. AB is the diameter of the circle. Okay. In the next step, we define angle PAM as alpha. This angle equals to alpha according to our definition. So in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in a triangle. We know that according to what is given in the question, PQ is a straight line. So if you focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PQ at point M? Here this angle is equal to 90 degrees minus alpha. This is the right angle. Plus this missing angle in total must be equal to 180 degrees according to rule 3. So remember that 90 degrees minus alpha plus 90 degrees plus this missing angle to the angle BMQ. Total, the sum of those three angles must be equal to 180 degrees according to rule 3. The upper side of the side line PQ at point M, the sum of the rest must be equal to 180 degrees according to all three. That is to say 90 degrees on alpha plus 90 degrees plus the missing angle BMQ total must be equal to 180 degrees. 90 degrees plus 90 degrees, it is 180 degrees, so we have 180 degrees plus the missing angle BMQ total must be equal to 180 degrees. Here also alpha here. Here we have 180 degrees both sides of the equation, so 180 degrees will get cancelled, and the left only once alpha plus the missing angle BMQ total must be equal to 0. Here we let alpha to the equation, and we get that the missing angle BMQ is equal to alpha. This is the missing angle BMQ is equal to alpha. So in the right side BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the rule that the sum of the angles in a triangle is equal to 180 degrees. Those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. In addition, those two angles are both equal to alpha, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So I can find out that all the figures of this right triangle EPM are equal to all the figures of this right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similarity rule. So I can know if you found out that the right triangle APM is similar. This is the sign of similar. So this right triangle MBQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of the small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BQM is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP equals to 9 over MQ. MQ is the missing side, so leave it as it is. And it is equals to PM. PM is the missing side, so leave it as it is. Over BQ. BQ is 4. So in total, I should find out that nine over MQ equals to PM over 4. Here we cross multiply this equation, and we get that 9 times 4 is 36 equals to MQ times PM. So I should find out that MQ times PM equals to 36. In the next step, we join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equals to R according to our definition. The radius OM is equals to R, the radius OM is drawn to point M, that is the point of tendency of tangent PQ with this circle. Remember, this is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say, from point O, that is the center of this circle, we'll draw perpendicular on AP. Again, from point O, we will draw perpendicular on AP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O, and AP, this point is point L. By doing this construction, we can do quadrangle LOMP. Quadrangle LOMP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 preceding, the total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4 preceding must be equal to 90 degrees in its size. So in quadrangle LOMP, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be this rectangle, not a square. So we write quadrangle LOMP is a rectangle because it has 4 right angles. So write it down, if you know that the big quadrangle LOPM is a rectangle according to rule 5. In the next step, we will do another construction, that is to say, from point B, we will draw perpendicular on the radius OM. Again, from point B, we will draw perpendicular on the radius OM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. When doing this construction, we get the small quadrangle SBQM. Inside the small quadrangle SBQM, we have 1, 2, 3 arteries. And therefore, this 4 pieces must be equal to 90 degrees in size. And therefore, quadrangle SBQM is rectangle according to all 5. So write it down. So remember that the small quadrangle SBMQ is rectangle. We know that the opposite sides of a square are parallel to each other. Okay, again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. And if a part of the straight line is parallel to another straight line, then the straight line itself, AP, must be also parallel to OM. Therefore, AP is parallel to OM. So write it down, that AP is parallel to OM. So in the next step, I'll copy the two parallel lines AP and OM, and also the radius AOB in the new page, and we'll implement all 50 on the drawing, the new drawing. Okay, this is line AP, this is parallel to line OM. AOB is the radius of the circle. Those two angles are defined as corresponding angles and they are located between the parallel lines AP and OM, and therefore they are equal to each other and their sizes. Only to all 50. Repeat this on all 50. Only to all 50 corresponding angles between parallel lines are equal to each other. In the drawing you have line A, this is parallel to line B. Line C cuts those two parallel lines at those 2 points. Those angles are alpha and beta, and they are defined as corresponding angles, and they are located between the parallel lines A and B, and therefore they are equal to each other, and their sizes. This is to say alpha equals to beta. So if we implement all 50 in our drawing, in our drawing, we have those two corresponding angles are located between the parallel lines AP and OM, and therefore they are equal to each other and their sizes. So if you define the size of this angle as beta, then the size of this angle must be also equal to beta, and therefore because they are equal to each other. So if you found out that angle PAO equals to beta degrees in size, this is angle PAO equals to beta degrees in size. Likewise, we also found that angle MOB also equals to beta. This is angle MOB, is also equals to beta degrees in its size. So in the right side, ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta. Likewise, in the right side, the ASB, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta. According to the rule that the sum of the angles in the triangle is equal to 180 degrees. So in the next step, I copy those two right triangles. This is not right triangle AO, this right triangle OSB in a new page. And we prove that those two right triangles can point to each other according to angle similarity rule. AO equals to OB equals to R. They're both there of the circle, therefore they're equal to each other. Okay, those are the two right triangles ALO and OSB that are going to the boring. So why those two right triangles can point to each other? First of all, both those triangles are both equal to beta and therefore they're equal to each other. Okay, this is again LAO. In the right triangle, ALO is equal to this angle, this is a triangle SOB. In the right triangle OSB. They're both equal to beta and therefore they're equal to each other. In addition, AO equals to OB, they're both the radii of the circle, this is equals to R and therefore they're equal to each other. AO equals to OB equals to R. And finally, those triangles are both equal to 90 degrees minus alpha and therefore they're equal to each other. So this is a triangle AOL. In the right triangle AO. And it is equal to this angle, this is a triangle OBS. The triangle OSB. They're both equal to 90 degrees minus alpha, and therefore they're equal to each other. So if you prove that those two right triangles can point to each other according to angle similar to. That is to say, if you prove that those two angles and the side that is included within those two angles in this right triangle OSB was probably equal to those two angles and the side that is included between those two angles it is right triangle ALO. Therefore, those two right triangles can go into each other according to angle similar to. So in the long we all know that the right triangle ALO congruent, this is the sign of congruent to the right triangle OSB according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that side LO of the right triangle ALO is equal to side SB of the right triangle OSB. According to the rule, the corresponding sides of congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, this is to say LO and SB, must be also equal to each other, and that. So SB equals to LO. Actually, found that SB equals to LO. So if we define the length of side SB is x, then the length of side LO must be also equal to x because they are equal to each other. So the big right triangle LO, the big right quadrant, the big rectangle LO and P, the opposite sides are equal to each other. That is to say, side LO equals to the opposite side PM. But LO is x, therefore the opposite side PM must be also equal to x units in its length. Likewise, in this whole rectangle SBQM, side SB must be equal to the opposite side MQ, but SB is x, therefore the opposite side MQ must be also equal to x units in its length. We have already found out that MQ times PM equals to 36. Meaning again, we already found out that MQ times PM equals to 36. MQ is x, PM is also x. So today we found out that x times x equals to 36. X times x is x squared, so x squared equals to 36. Here we take out of the equation and find again that x equals to the square root of 36, that is 6. So x equals to 6 units in its length. Here x equals to 6. Here x equals to 6. In the next step, we implement the Pythagoras theorem on this right small triangle MBQ. So we call it right small triangle MBQ in the equation. We implement only the Pythagoras theorem. So here this is right triangle MBQ to the corresponding module line. This right triangle MBQ, according to the Pythagoras theorem, we get that BM square equals to MQ square plus BQ square. So if you don't know that BM square, that is the square of the hypotenuse, equals to BQ square plus MQ square. PM is the missing side, so so PM square equals to BQ square. BQ is 4, therefore BQ square is 4 square, that is 16, plus MQ square. MQ is 6, therefore MQ square is 6 square, that is 36. So to that, we show that BM square equals to 16 plus 36, that is 52. So BM square equals to 52. Here we take root out of the equation and finally get that the missing side BM, the missing hypotenuse BM is equal to the square root of 52, the square root of 52 units in its name. This is side BM. Is equal to the square root of 52 units in its length. In the next step, I'll copy that in the right rectangle APM and in the equation we'll implement the Pythagoras theorem. So this is right by APM, the corresponding point is right by APM. AM square, that is the square of the hypotenuse, equals to AP square plus PM square. So write it down. Remember that AM square, that is the square of the hypotenuse, is equal to PQ to AP square plus PM square. AM is the missing side, so it is AM square equals to AP square. AP is 9, therefore AP square is 9 square, that is 81. Plus PM square. PM is 6, therefore PM square is 6 square, that is 36. So to that, if you remember that AM square equals to 81 plus 36, that is 117. So here we take out of this equation and get finally that AM equals to the square root of 117 units in its length. So here this is side AM, that is equal to the square root of 117 units in its length. Now it asks you to find out this green white triangle A and B. We know that the area of green triangle equals to the base of the triangle times the height over 2. Therefore, the area of the green white triangle A and B must be equal to the base MB times the height AM over 2. Again, this is what AM equals to the base MB times the height AM over 2. We only found out that MB equals to the square root of 52 units in this line times AM equals to the square root of 117 units in this line divided by 2. So we found out that the other AM equals to the square root of 52 times the square root of 117 over 2. Here we have the algebraic identity. It says that the square root of A square root of A times square root of B equals to the square root of A times B. According to this algebraic identity, we get that square root of 52 times square root of 117 is equal to in total to the square root of 52 times 117. Yes. Divided by 2. 52 times 117, 6084 divided by 2. The square root of 684 is 78 over 2. 78 over 2 is 9. So do that, actually found out that the area this ratio, the area that you're looking for is equal to 39 squares in size. This is the answer to the question. Okay, again. The area of this ratio equals to 39 squares in size. So we finish with the first question. In the next step of some other lecture, we'll start with the first question, of course. In the first question, our task is to find out the area of this pentagon ABCDE. So, what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interlagers. This is pentagon ABCDE. It is 5 sides: 1, 2, 3, 4, 5, and 5 interlagers: 1, 2, 3, 4, 5. So, in the drawing, we have pentagon ABCDE. You know that EO equals to BC equals to EA equals to 1, DC equals to X, AM equals to 1 on 6. This is angle EAB, this is right angle. This is angle EDC, this is also right angle. Again, our task is to find out the area of this big pentagon ABCDE. So first of all, we join points C and B together by a straight line. We join points C and C together by a straight line. Then we extended side VA of this pentagon ABCDE by a straight line in such a way that the extended part that is actually MA equals to X units in select. So MA equals to X according to our construction. We know that when we set a straight line by straight line, the result is a straight line. Therefore, BM is a straight line. So if you focus on the upper side of the straight line BM at point A here, the sum of the areas must be equal to 180 degrees according to all three. All three said that the sum of the areas from one side of the straight line is equal to 180 degrees. So which areas we have at the upper side of the straight line BM at point A, we have this area, this is the right angle, plus this missing angle must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we prove that the green tire EMAs convert to the green tire EDC according to side angle side all. So for those two tires in the present, we prove that they convert to each other. Okay, those are the two tires EMA and ECD to the point of the original drawing. So why those two tires convert to each other? First of all, we found out that those two sides are equal to each other. Yep, those two sides are equal to each other. First of all, we found out, we know that MA equals to CD equals to X. Again, side MA of the right side EMA is equal to side CD of the right side EDC. They are both equal to X and therefore they are equal to each other. In addition, those two areas are both equal to 90 degrees and therefore they are equal to each other. And finally, EA equals to ED equals to 1. And again, EA equals to ED equals to 1. So they are both equal to 1 and therefore they are equal to each other. So if you put that those two right areas convert to each other according to side angle side rule. That is to say, those two sides and the angle that is included between those two sides in the right tire EAM are corresponding equal to those two sides and the angle that is included between those two sides in the right tire EDC. And therefore, those two right tires convert to each other according to side angle side rule. And from the fact that they convert to each other, we know that they are also the same areas. That is to say, the area of this right triangle EMA is equal to the area of this right triangle EDC. So we define the area of this triangle as Z, then the area of this right triangle EMA must be also equal to Z squared in size. In addition, from the fact that those two right triangles convert to each other, we arrive that EM equals to EC. Again, EM equals to EC. In the next step, we calculated the log of MB. MB equals to MA plus AB. Again, MB equals to MA plus AB. MB equals to MA, that is X, plus AB, that is 1. So in total, MB equals to X plus 1 minus X. X minus X is 0, so MB total equals to 1. The next step, we prove that triangle MEB can go into this triangle EBC according to side 1. So for those two triangles in an equation, we prove that those two triangles can go into each other. Those are the two triangles that go into the original drawing. So when those two triangles can go into each other, first of all, those two sides are both equal to 1 and therefore they are equal to each other. That is to say, AB equals to BC equals to 1. In addition, those two sides are also equal to each other. Therefore, EA equals to EC. And finally, EB is a common side that belongs to both triangles. Therefore, EB is a common side that belongs to both triangles. So if you find out that EB equals to itself, it's a common side that belongs to both triangles. So if you find out that all the triangles of this triangle EMB are corresponding equal to the triangles of this triangle EBC, and therefore those two triangles can go into each other according to side rule. And from the fact that they go into each other, we derive that they are also the same areas. That is to say, the area of this triangle MEB is equal to the area of this triangle BBC. Again, the area of triangle EBM is equal to the area of triangle EBC. The next step we calculate the area of this triangle EBM. The area of this triangle EBM will be equal to the base EB times the height AE over 2. Again, the area of triangle EBM equals to the base MB times the height EA over 2. MB is 1, AE is also 1, so MB times EA is 1 times 1 divided by 2. 1 times 1 is 1, so 1 over 2. So if you found out that the area of this triangle MEB is equal to half square units in its size. The area of triangle MEB equals to 1 half square units in its size. And from this, so you can write here that the area of triangle EB equals to half square units in its size. So from this equation, 1 half equals to the area of triangle EBM equals to the area of triangle EBC. We derive that the area of triangle EBC equals to 1 half. So in total, the area of this triangle EBM plus the area of this triangle EBC will be equal to 1 half plus 1 half, that is 1. The area of triangle EMB plus the area of triangle EBC in total equals to 1 half plus 1 half, that is 1. So the area of those two triangles is equal to 1 half square units in size. But quadrilateral EMBC consists those two triangles. Quadrilateral EMBC consists triangle BEM, and it is also consists triangle EBC. And therefore, the area of quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this triangle MEB, this is 1 half, plus the area of this triangle EBC, this is also 1 half. 1 half plus 1 half is 1. So in total, we found out that the area of this big quadrilateral EMBC equals to 1 half square units in size. The big quadrilateral EMBC equals to 1 square units in size. But the big quadrilateral MEBC consists of two other shapes. It consists of this green triangle EMB and this quadrilateral ABCE. And because of the fact that the area of the big quadrilateral EMBC equals to 1, it means that quadrilateral EBC consists of those two shapes. It means that the sum of the areas of those two shapes will be equal to 1. Because the area of quadrilateral EBC is equal to the sum of the areas of the two shapes that it consists of. So the area of the green triangle EMA plus the area of quadrilateral ABCE will be equal to 1. The area of the green triangle EAM plus the area of quadrilateral ABCE equals to 1. Okay. But we already found out that the area of this quadrilateral AEM is equal to Z according to our construction. So you can consider the area of quadrilateral EAM by Z, and you get that total Z plus the area of quadrilateral ABCE equals to 1. Okay. Our test is to find out the area of this pentagon ABCDE. From the drawing, it is very easy to say that pentagon ABCDE consists of two shapes. It consists this green right triangle EDC. It also consists this quadrilateral ABCE. Therefore, the area of pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of pentagon ABCDE equals to the area of quadrilateral and the area of triangle EDA plus the area of quadrilateral ABCD. But we already found out that the area of this green right triangle EDC is equal to Z. So you can solve the area of triangle EDC by Z, and you get that total the area of pentagon ABCD must be equal to Z plus the area of quadrilateral ABCD. But we already found out that the area of quadrilateral Z plus the area of quadrilateral ABCD equals to 1. So we can substitute Z plus write down that Z plus the area of quadrilateral ABCD equals to 1. And from this equation, we derive that the area of pentagon ABCD equals to 1 square units in size. Area of this pentagon ABCD equals to 1 square units in size. So we finish with the first question. The next step I presented to the second question, and we solve the second question of this lecture. The second question, our task is to find out the area of this great shape. The great shape is actually triangle, so we have to find out the area of triangle A and B. So in the following we have a circle. This gives us the question that AB is the diameter of this circle. In addition, we know that AP equals to 9 units in its length, PQ equals to 4 units in its length. This is again APM, this is right angle, this is again BQM, this is also right angle. Again, our task is to find out the area of this grand triangle A and B. So, first of all, we can implement all 7 in our drawing. Why? Because we have triangle A and B that subtend on AB to the diameter of the circle. And according to all 7, any triangle that subtend on the diameter of the circle must be equal to 90 degrees in size. So triangle A and B equals to 90 degrees in size. It is given as a question that PQ is a straight line. So if you focus on the upper side of the straight line PQ at point M, if the sum of the areas must be equal to 180 degrees according to all three. All three said that the sum of the areas on one side of the straight line is equal to 180 degrees. So which areas we have the upper side of the straight line PQ at point M? Actually, before that, we define this angle as alpha. So in the right hand APM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees plus 280 degrees. That is the sum of the areas in a triangle. So we know that the sum of the areas of the upper side of the straight line PQ at point M must be equal to 180 degrees according to all three. So 90 degrees plus alpha plus 90 degrees plus the missing angle BMQ total must be equal to 180 degrees. So then I can solve with 90 degrees minus alpha plus 90 degrees plus the missing angle BMQ total must be equal to 180 degrees according to all three. So here we have 90 degrees plus 90 degrees is 180 degrees. So we have here 180 degrees minus alpha plus angle BMQ in total must be equal to 180 degrees. We have 180 degrees on both sides of the equation, so 180 degrees will get cancelled, and left only minus alpha plus the missing angle BMQ equals to 0. Here we added alpha to the equation and find out that the missing angle BMQ equals to alpha. This is the missing angle BMQ is equals to alpha. So in the right angle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and all this first missing angle must be equal to 90 degrees minus alpha. According to the rule that the sum of the areas in the triangle is equal to 180 degrees. The next step we prove that the right triangle APM is similar to the right triangle BMQ according to angle similar to. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you follow that all the triangles of this big right triangle APM are corresponding equal to all the triangles of this one right triangle BMQ, and therefore those two right triangles are similar to each other according to angle similar to. So we should find out that the right triangle, the big right triangle APM is similar to the small right triangle MBQ according to angle similar to. And from the fact that they are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of the small right triangle BMQ. Again, AP over MQ equals to PM over BQ. AP is 9 over MQ. MQ is the missing side, so it is. And it is equals to PM. PM is the missing side, so it is. Or BQ. BQ is 4. So if you follow the 9 over QM equals to PM over 4. If of course multiply this and follow that MQ times PM equals to 9 times 4, that is 36. So 36 equals to MQ times PM. The next step, we define the center of this figure. This point is point O. O is the radius is equal to R according to our definition. O B is also the radius, so this is R. The next step, we join points O and M together with a line. Point O is the center of the second, point M is the point of the second itself, therefore OM is the radius of the second is equal to R. Here we can implement all 1. We have the radius OM that is equal to R. The radius OM is going to point M, that is the point of tendency of tangent PQ with this circle. And whenever your radius is going to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this area equals to 90 degrees, and this area equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say from point O, that is the center of the circle, we draw perpendicular on AP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point O in AP. This point is point L. By doing this construction, get this quadrilateral LOMP. Quadrilateral LOMP, we have 1, 2, 3 vertices, and therefore this 4 pieces must be also equal to 90 degrees in size. According to the rule, the sum of the angles in any quadrilateral is equal to 360 degrees. And because of the fact that quadrilateral LOMP is 4 vertices, we relate to quadrilateral LOMP is a rectangle. In the next step, we did another construction, that is to say from point B we draw perpendicular on the radius OM. Again, from point B we draw perpendicular on the radius OM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OM. This point is point S. By doing this construction, we get that quadrilateral SBQM. Quadrilateral SBQM is 1, 2, 3 vertices, and therefore this 4 pieces must be equal to 90 degrees in size, and therefore we can erase quadrilateral SBQM is a rectangle because it is 4 vertices. We know that the opposite sides of a rectangle are parallel to each other, so in the big rectangle LOMP, side LP must be parallel to the opposite side OM. But LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, then the straight line itself, AP, must be parallel to OM. So AP is parallel to OM. In the next step, we commit the two parallel lines and the radius AB. In the equation, we represent rule 50 in the following. This is side AP, this is parallel to side OM, and this is the radius AOB. This is going from the original line. Those two angles are defined as corresponding angles, and are located between the parallels AP and OM, and therefore they are equal to each other according to rule 50, that says that corresponding angles between parallels are equal to each other. Therefore, those two angles are equal to each other in their sizes. So if you define the size of this angle is beta, then the size of this angle must be also equal to beta. So if you found out that angle PAO equals to beta, this is angle PAO, this equals to beta, and angle MOB is also equals to beta. So in this triangle OSB, this angle equals to beta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees. Beta. Likewise, in the right triangle ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus beta. In the next step, we commit those two right triangle ALO and OSB. In the equation, prove that those two right triangles can go into each other according to angle side and angle rule. Okay. Those are the two right triangles ALO and OCB, that are going to the original drawing. So why those two letters can point to each other? First of all, those two angles are both equal to beta and therefore they are equal to each other. In addition, AU equals to OB, they are both the radius of the second is equal to R, therefore they are equal to each other. Find those two angles are both equal to 90 degrees also, find therefore they are equal to each other. So we should hold that those two letters can point to each other according to angle side angle rule. That is to say, hold that those two angles and the side that is included between those two angles in triangle A and O are corresponding equal to those two angles, and the side that is included between those two angles, that is OB, in the right triangle OSB. Therefore, we hold actually that those two right triangles can point to each other according to angle side angle rule. Okay. And from the fact that they can point to each other, we derive that LO equals to SB. According to the rule, the corresponding sides in the one triangles are equal to each other. Those two triangles can point to each other, and therefore the two corresponding sides LO and SB must be also equal to each other in their sizes. So if you find LO is X, then SB must be also equal to X because they are equal to each other. So SB equals to LO. So if you define side SB is X, then side LO must be also equal to X because they are equal to each other. So LO equals to X and SB equals to X. We know that the opposite sides of our triangle are equal to each other. So the big triangle LO and P, side LO is equal to the opposite side PM. But LO is X, therefore the opposite side PM must be also equal to X units in its life. Likewise, in the small of triangle SPQM, side SB equals to the opposite side MQ. But SB is X, therefore the opposite side MQ must be also equal to X units in its life. We already found out that MQ times PM equals to 36. MQ is X and PM is also X. So we found out that X times X equals to 36. X times X is X squared, equals to X to 36. Here we go to out of this equation and I found out that X equals to the square root of 36, that is 6. So here X equals to 6 and here also X equals to 6. And the next step we copy the right small triangle MBQ and then we implemented on this small right triangle MBQ the bottom also one. This is the small right triangle MBQ that the copy from the original drawing. This small right triangle MBQ contains the bottom also one, big M squared, this is the square of the product, equals to big Q squared plus MB squared. BM is the missing sign, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16, plus MQ squared. MQ 6, therefore MQ squared is 6 squared, that is 36. So in total, if you want out that BM squared equals to 16 plus 36, that is 52. BM squared equals to 52. You have to go out of the equation and find out that BM equals to the square root of 52 units in its length. This is side BM equals to the square root of 52 units in its length. In the next step, we'll copy the right triangle APM in the new page and we implemented on this right triangle APM the brother also. This is the right triangle APM that the copy from the original drawing. This right triangle APM according to the brother also one, AM squared, that is the square of the opponent, equals to AP squared plus PM squared. AM is the missing side, so it is and it is equals to AP squared. AP is 9, therefore P squared is 9 squared, that is 81 plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, AM squared equals to 81 plus 36, that is 117. So AM squared equals to 117. You have to go out of this equation and find out that AM equals to the square root of 117 units in its length. This is side AM that equals to the square root of 117 units in its length. Our test is to find out the area of this range shape that is actually the right triangle AMB. You know that the area of any triangle equals to the base times the height over 2. So the area of this right triangle AMB will be equal to the base MB times the height MA times 2. The area of the right triangle AMB is actually the area of the range shape equals to the base MB times the height AM over 2. We only found out that MB equals to the square root of 52 units in its length and AM equals to the square root of 117 units in its length. So again, b equals to the square root of 52, and m equals to the square root of 117 units in its left, divided by 2. We have the algebraic identity that says that the square root of a times the square root of b equals to the square root of a times b. According to this algebraic identity, we get that the square root of 52 times the square root of 117 equals to the square root of 52 times 117. Here we have to divide it by 2, and 52 times 117 is 684. Divided by 2. The square root of 684 is 78 divided by 2. 78 over 2 is 39. So to that we should remember that the area of this ring shape, that is the area that we are looking for in this question, is equal to 39 square units in its size. Okay, thank you very much.